In section 3, we are going to look at our last test for chi-square, and that's the test for association/independence. So far, we've talked about the chi-square goodness of fit, which is used to determine if a claimed distribution for a single categorical variable is what is observed. And usually data is given in a one-way table, or you can organize it as one. Then we talked about the chi-square test for homogeneity, which takes separate random samples or multiple treatments, and it tests to see if a distribution of categorical variables is the same for each of several populations or treatments. So you're looking at multiple populations. Now we're going to talk about the chi-square test for association/independence. And what it does is it takes a single random sample of individuals and classifies them according to two categorical variables. And the goal is to analyze the relationship between the two variables. And again, we are going to be given a two-way table to look at our data. So when we're performing this test, you have to be careful because it's run in almost the exact way as the chi-square test for homogeneity, and the difference comes in what the question is asking and where the data is coming from. So our null hypothesis is that there is no association between the two categorical variables in the population of interest, and our alternative hypothesis is that there is an association between the two categorical variables in the population of interest. So if we have no association between our two variables, that means that the values of one variable do not tend to occur in common with values of the other. That is, the variables are independent. Therefore, another way you can write your hypothesis, so your null hypothesis can be two categorical variables are independent in the population of interest. And we can think of our alternative hypothesis as two categorical variables are not independent. In the population of interest. When it comes to conditions, it's the exact same conditions we were dealing with before, so we just assume all of them are met. And the way we do our expected counts, our statistic, degrees of freedom, and p-value are all calculated the same way as the chi-square test for homogeneity. And then the conclusions will be interpreted in the same manner but adjusted for the new hypothesis. So in our example, we have that a study followed a random sample of 8,474 people with normal blood pressure for about 4 years. All the individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale test, which measures how prone a person is to sudden anger. Researchers also recorded whether each individual developed coronary heart disease, or CHD. This includes people who had heart attacks and those who needed medical treatment for heart disease. Here is a two-way table that summarizes the data. Do the data provide convincing evidence of an association between anger level and heart disease in the population of interest? So what we're dealing with here is a single sample because we only have one group of people, but we are looking at multiple variables within that one group. So for our null hypothesis, we'll write there is no association between anger level and heart disease. And then our alternative hypothesis will be there is an association between anger level and heart disease. So now we're going to go ahead and fill out our table of expected values. So like we said, we calculate those the exact same way we did in section 2. So we take our row total times our column total and then divide by the population total. So for the expected blood pressure level of low, we take 190 times 310, and then we'll divide by 8474 for the CHD row, and we'll get 69.7. For moderate, we do 190 times 4,731, and then we'll divide by 8474, and we get 106.1. And then for high, 190 times 633 divided by 8474, which is 14.2. So for our row for no CHD, we'll take 8284 times 3110, then divide by 8474, and we'll get 3040.3. For moderate, it's 8284 times 4731 divided by 8474, which is 4642.9. And then for high, 8284 times 633 divided by 8474, which is 618.8. Now we can go ahead and calculate our chi-squared statistic. So we're going to take 53 minus 69.7 squared over 69.7 plus 110 minus 106.1 squared over 106.1 plus 27 minus 14.2 squared over 14.2 plus 3,057 minus 3,040.3 squared over 3,040.3. Then 4621 minus 4642.9 squared over 4642.9. And then our last value, 606 minus 618.8 squared over 3040.3. So that's going to give us a chi-squared test statistic of 16.08. So for our p-value, we need our degrees of freedom. So our number of rows, 2 minus 1, times our number of columns, 3 minus 1, is going to give us degrees of freedom of 2. And then when we go to second bars, we go to 8, and our lower bound will be 16.08. Our upper bound will be 1E99. Then our degrees of freedom 2. And when we calculate it, we're going to get a p-value in scientific notation. It should be 3.23, and then you should have the e-4. So it tells me I have 3 zeros and then 3, 2, 3. Okay. So now I need to compare our p-value to our alpha, which is not stated in the problem, so we know we're going to be using 0.05. So this is obviously less than our alpha of 0.05, which means we reject our null hypothesis. So that means for our sentence, there is evidence to show that there is an association between anger level and heart disease among people with normal blood pressure. So let's go ahead and talk about a couple things about making sure you're using chi-square correctly. So the chi-square test for homogeneity and the chi-square test for association or independence are very, very similar. They both start with a two-way table as observed counts. They calculate a test statistic, degrees of freedom, and a p-value in the same way. However, the questions that these two tests answer are different, and that's where you have to know which one you're performing. So a chi-squared test for homogeneity tests whether the distribution of a categorical variable is the same for several populations or treatments. So you're looking at multiple populations in a chi-square test for homogeneity. In a chi-square test for association or independence, you're looking at two categorical variables within the same population of interest. So it's whether or not you have one population or multiple population. So instead of focusing on the question that's asked, it's much easier to look at how the data were produced. Obviously, if the data comes from one independent random sample with multiple categories, that's a chi-square goodness of fit. So if we go back to section 1, the mice and eye color example. If you have data that comes from 2 or more random samples or treatment groups, then you have your chi-square test for homogeneity. So that was our gender and living situation. So we had 2 different populations, male and female. And then if the data comes from one random sample, but the individuals were classified according to 2 categorical variables, then we use a chi-square test for association or independence. So that's our anger and CHD example that we just did. We have one population, but we have 2 different categorical variables. So let me know if you have any questions about the chi-square test for independence or homogeneity, or being able to tell which chi-square test you are going to perform.